Good morning, students. Yesterday, we have calculated the gravitational potential at a point outside the spherical shell. Now, in today's period, we'll derive the equation for gravitational potential at a point inside the spherical shell. For this, we'll consider this type of a spherical shell. Now, in this spherical shell, the point P is situated inside the spherical shell at a distance r. The from center O, where the radius of this spherical shell is capital R. Now CE now we cut the shell in this slice. That slice is CEDF. We can cut like this number of slices and calculate the gravitational potential for this slice on this point P. Now then we can integrate and calculate the gravitational potential for total spherical shell. Now in yesterday's period we have calculated the potential at a point due to this slice. The potential at a point P due to the slice or ring. Slice or ring. This slice. This is the slice. This slice is nothing but a ring, and we have calculated the potential at a point due to this slice, and it is given by the formula dV equals to 2 pi r minus 2 pi r rho upon r into gdx. In yesterday's period we have derived this formula. Today what we have to do, we have to take the integration for this. Now the integration can be taken in the points, that is the limits are r minus r, because the radius of this sphere is capital R. That can be shown here, the radius of this capital R, and this point P is inside the cell. Therefore the upper limit is minus r and the lower limit is, and we can write it like this, taking the integration of x r minus r and r plus r. Now integrate this equation, we have now, for if we integrate dt, then it will become v, and integration from r minus r to r plus r, 2 pi r rho upon r into g dx. Here we'll take the constant term outside the integration side. The constant terms are 2 pi r rho upon r into g. All these are the constant terms, and inside the integration side, the remaining part is only dx. That is dx. If we integrate dx, we'll get x. Therefore, d equals to 2 pi r rho upon r into g. This is x and its upper limit is r plus x and lower limit is r minus x. R minus r plus r and r minus r. Therefore, this can be written as v equals to 2 pi r rho g into r into the. First of all, we'll write the upper limit in place of x and then minus lower limit here. Here this plus r and minus r will get cancelled and inside the sign we therefore we get like these terms v equals to 2 pi r rho g in divided by r into 2r. This 2r will get cancelled and lastly we get 2 into 2 is 4 pi r rho g. 2 pi r rho g. Multiplying for here for this equation we made one adjustment and that adjustment is multiply and divide by capital R, that is this radius R. Therefore multiplying and dividing by R we get, that is v equals to 4 pi r square rho into g upon r. But we know that the mass of this spherical cell is given by the formula, that is but 4 pi r square rho 4 pi r square rho equals to 4 pi r square rho equals to the mass of this total spherical cell. Therefore, this equation becomes v equals to m v equals to minus m g upon capital R. And this equation gives us the gravitational potential at a point inside the spherical cell. Here, this equation, in this way, we have calculated the potential for the spherical cell when point P lying inside the spherical cell. Now, the second case is the gravitational potential due to the spherical cell. Gravitational potential at a point we have calculated outside, we have calculated inside, and then next case is gravitational potential on the surface of the spherical cell. In this way, we have calculated for the point lying on the surface of the spherical cell, we have to differentiate or integrate this equation in the limits of from r to r only. The next point is on the spherical cell. Here, this point P is lying on the surface of this spherical cell. When this point is lying on the spherical cell, then we have to integrate the equation for here the radius of this spherical cell and the distance between O and this point P is r. Means here r equals to capital R and the limits we have to take, means we have to integrate the potential from R to twice of R. Therefore, we can write that equation like this: dV equals to 2 pi r rho 2 pi r rho upon r into g dx. Now integrating this equation from, therefore v equals to r 0 to 2r 0 to 2r 0 to 2r, as the value of this r, when it is very small slice is taken, then the distance of this r is nearly very close to the g. Therefore, we have taken here this limit r equals to 0 to 2r. Now, inside the integration sign 2 pi r rho upon r into g dx. Now, we have to integrate this. For integrating this, as we have integrated it, then this constant term have to take outside the integration side and integrate other terms in the limits 0 to 2r dx. This can be written as v equals to minus 2 pi r rho g upon r into x raised to 0 to 2r. Therefore, v equals to minus 2 pi r rho g upon r into x equals to only 2r minus 0, and this lastly we get v equals to minus 2 pi r, 2 into this 2, it becomes 4 pi r square rho g upon r. But we know that 4 pi r square equals to the mass of the, but we know that 4 pi r square rho equals to m. Therefore, this equation becomes v equals to minus mg upon r. This is the potential due to the spherical shell when point P lies on the surface of the spherical shell. In this way, we have completed the three cases when we have calculated the gravitational potential for the point lying outside the spherical shell, and in the second case when point P is lying inside the spherical shell, and lastly this third case the when point P lies on the surface of the spherical shell. In this way, we have calculated the potential at a point due to this spherical shell. And in the next period, we will see the gravitational intensity. Today we will stop here.